Okay, we're rolling. So we've got Mipar open here. Again, this is the second public Mipar webinar. We're going to first go through just an overview of the software. I'll open up each of the applications and just give an explanation of what they do with some example data. So the image processor is where a number of us spend the majority of our time. This is single image analysis and recipe building. Your recipe is probably the most important tool in Mipar, and it's a sequence of image processing steps that aim to identify features of interest and then measure them. So the demo image I'll use to go through this app, the image processor, is just a pretty basic SEM image of some composite material with reinforcement particles and matrix. And I can load in a recipe that I've made here. Or build one from scratch. So that's the end result. We can click through the steps here and see what happened. Here was a global threshold step. You know what, I will actually go ahead and well, we'll do this during the segmentation part. We'll go and build one of these up from scratch. But your recipe panel here is where you navigate through the steps. So double-clicking on a step lets you see the result of it. The same can be accomplished by right-clicking and hitting Show, or clicking the Show button down here. So the approach here was roughly find the particles with a global threshold. You can always go back and edit those parameters. We picked a value that was somewhere in the middle of the histogram here, or you can auto and let the tool try to decide the best parameter. And then with this being an auto step, every time the recipe is run, the value might be calculated a bit differently from image to image. So it makes it flexible. Manual will fix the value there. And then we went and we did a cleanup step where we got rid of some of the black noise particles. Same thing for the white ones. We rejected some small black features that we didn't want. And then it's important to remember that in Mipar, the selection in your image is black. That's the convention. So we flipped it around so that we've told Mipar the particles are what is selected. And then we put this in memory. We went and we just kept the smaller features because we wanted to run a separation routine on the bigger ones called a watershed, but sometimes that does some weird things to the small ones. So we put away the small ones in a different memory slot called a companion image, and then we went back to this restore image 1 and we ran our separation routine that cut these particles. And you see it did do some strange things to some of the smaller ones. I don't know if I have an example of that. Yeah, this one here got split up strangely from the watershed. So then we just combine this image with the darker pixels from this image, which is what this keep darker pixel step does. So we go from that to that, and then we combine back those smaller ones so they're not separated. And that's our grain selection here, and then we just invert to get the matrix. So that's running a recipe, that's navigating through it. Like I said, always go back and edit a step. Let's say we want the threshold to be like this instead. Click accept, and now the rest of the recipe gets re-executed, so that change propagates through. Same thing with removing a step. If you want to insert another one, whatever step is highlighted, the next step will go underneath that. So if I wanted to put a erosion step of some kind underneath this one, I just pick the step and choose the parameters and hit accept. Now that goes underneath and the rest gets executed. If you're on the top step, you get asked, do you want to put the next one above or below, just so that you can put it above the top step if you need to. And then we'll remove that step and see the rest of it get repeated. Now in the latest pre-release, 5C of Beta 7, we introduced it in 5A, and then there have been 2 patches. but we're now on 5C, which hopefully you're running. And again, the full beta 7 should be out mid-July. We did finally have the ability to select and remove multiple steps. When you select multiple steps, all but a couple controls dim out to show you what you can do. And clicking on this disable step here will go and disable all recipe steps below what you've selected, so that if you were to insert now another step, the rest of the steps just get quickly passed over to make sure there are no errors, but they don't actually get re-executed. So it lets you quickly add steps to the recipe. And now it's giving me an error there. Okay, so it looks like I may have uncovered a bug, of course. I will show that feature, I guess, on a different recipe, but it's supposed to, you're allowed to disable steps so that they're not auto-updated, and it lets you fiddle with steps higher up in a recipe without waiting for the entire thing to update. And then, of course, at the end, you probably want to re-enable those so that you get the most up-to-date recipe, but that's been a requested feature for some time. And then finally a clear recipe button that lets you clear out the entire thing and start over if you want to. Let me just build one up here a little bit quickly to show that feature without that problematic step here. Reject these small white features, find out what size they are, so we'll just take our ruler tool and double click on a small one and say, okay, get rid of any white features that are under 25. And okay, so now let's put one more step here at the end. That's too much. So if you just wanted to be messing with this one value, or and just have this one update but not the rest, then you would just disable the auto update from this point down, and then when you go in here and fiddle with this parameter, just that step gets updated. The rest get checked for errors, but they're not actually executed. So then when we do this, changes to enable here up, so if you click this now, from there up everything gets re-enabled, and the ones that were disabled get redone, so they're up to date again. So it can help you work on a long recipe if you're messing with steps early on. And then finally, layers. So once you have your recipe built, and I should, I guess, mention these different overlay modes can be very handy. We've been working in black and white view the entire time, but we can switch to an overlay mode where you have a translucent overlay of the segmentation on the original or on the reference image. Outline is probably my favorite, and then labels is just a random coloring of the separate features with, changeable opacities. So let me just throw a watershed step here to separate. 3 is usually a good starting point. You can see from the separation step, we've gone from a lot of clusters now to a separated set of, or a more separated set. And now I'll just invert, so we have the matrix here. So what I'd probably want to do is say, okay, here's my whole recipe. These last 2 steps are really what matter. So I can go and say, you can do this a couple of ways. You can either go right into your layers interface here that gives you your recipe, and you can select any of these steps and see what that step did. And you can say, okay, my watershed step here I'm going to call my grains. So add this as a layer, call it grains, and then take my inverted thing here, add this, and call it my matrix. So now you can view multiple steps overlaid on each other with different colors, set the opacity against the reference. But now that these steps are layers, this gives us a couple of advantages. Let's save these and close. So they're indicated with their name here and a star to show that it's a layered step. So if we added a measurement now to the recipe, and it's worth mentioning that only global measurements can be added to a recipe. If you want feature by feature measurements like the area or the diameter of every feature, that is something that does not get added as part of the recipe, but you can still make those measurements on a batch of images in the processed image editor. But we are working on adding feature measurements as a step in a recipe. But right now we only have global in there. So if we added a global measurement like area fraction, since, well, you can generate a report even if you don't have layers, but that's going to just conduct the measurement on the last step of the recipe. With layers set, if you generate a report, you'll get now all of these measurements down here performed on every step that is set as a layer. So that's one advantage. If you run this recipe as a batch, you'll get the black and white image for every layer saved as an image, and then you can read all of those in to the purple application to click through each image and see how the different layers were segmented. I'll show that here in 1 second. And then finally, if you're working with 3D, any steps that are set as layers in a recipe, when that recipe is run to build up a reconstruction, you'll get 3D layers in your reconstruction for each segmentation. So layers are sort of favoriting steps that then give you some advantages. So we have global measurements there. If we wanted to quickly view, let's say, the diameter of all these particles over on a color scale, then we could go right into the color by measure tool and generate, let's say, diameter measurements of everything. And then those get loaded right in here as in a table, so you have the diameter of every feature. And if you just click any cell in any column, the column determines what values are used for the colorization, and the row determines what feature gets highlighted. I'm just going to pick any column in the diameter column, or any row in the diameter column, and now all the particles are colored according to diameter, and whatever row you pick highlights that particular feature. Or you can hide that if you want. So that's quickly coloring by some measurement. And yeah, that's probably a decent overview for the image processor. Calibrating your magnification is something you need to do if you want to make measurements in physical units like microns instead of pixels. I don't think I have this image with a scale bar on it, but if you did, or you had an image that was taken at the same magnification and pixel dimensions that had a known distance on it, like a scale bar, then you would just pick that image. So let's say that magically I know this is 10 microns across, but imagine it was a scale bar. So I'll put that there and say that's 10 microns. And now you have a microns to pixel calibration factor that is part of the recipe. So measurements that you make now would be in microns instead of pixels. And if you saved this recipe with that factor present, that factor is part of the recipe now. So if I cleared this out and then loaded the recipe back in, that factor would come with it. We've got some integrated help here. You'll see that in the image processor and the 3D tool. All other elements are tool-tipped, so you get some indication of what they do. If we wanted to move on, are there any questions at this point, or I'll move on to the batch processor and the processed imager to show other parts of the 2D workflow. I'm good so far? Okay. So I don't have multiple images of this, but I do have them for a different microstructure. So let me, this was a new feature that's part of pre-release 5 of beta 7 now, is you have the option to reload a different image. Let's say this was a different image, and then just have that recipe get automatically rerun on it. So it saves you a couple of steps if you're testing out how the recipe behaves from image to image. So let's get a new one in here. I'm going to take one of these gamma prime on gamma matrix images and just show you the recipe that I made for this. I guess we'll ignore the scale bar for now. I thought I had. No, the others don't have micron bars. That's what it is. So open one of these other ones. We have 2 layers in this one. If we want to look at them, hit layers. We've got the smaller precipitates that are the tertiaries in red, and the secondaries in green. You can look at that as an outline too if you want. So let's say we wanted to run this recipe on a number of images, and we also wanted to get the I don't know, area fraction of each layer. So I'm just going to add an area fraction measurement to the recipe here, and we'll save this as a new one that's with layers and measurements. And now we can either launch the batch processor and load the recipe manually, or if you launch it from the image processor, it will bring in the last saved recipe for you. And we're just going to pick where to save the processed images. I'll just put them right here in this folder. Instead of processed, I'm going to give them the suffix segmented. And then we're just going to pick these 5 images to run. You don't need to, I didn't calibrate the magnification in this case because we're only measuring area fraction, which is a 0th dimension quantity. So what is being output as you run, you've got a folder here that is named whatever you chose the suffix to be inside of your save directory. You see for each image we're getting a secondary and a tertiary image because we have a secondary and a tertiary layer as part of the recipe. And then also in that save directory we've got measurements for each layer. So we open this up in Excel. For every image, here is the secondary area fraction, and then we have the same for the tertiary. You can generate global measurements like that directly from a recipe by having a recipe or a measurement step in the recipe, or as you'll see in a second, we can do the measurements after segmentation once we've had a chance to review and make sure that the segmentations aren't way off. So once the batch is run, we can just say review processed images, and that'll bring everything into the processed image editor for our review. So now we have our black and white images that have been loaded in automatically. We have the reference images, and we've got our layers management. So we have tertiary and secondary layer available. If we switch to secondary, that'll read in the secondary measurements, and we can click through each image and see how the secondary finding worked. Or we can switch to tertiary just to look at them. Or you can view in layers mode, and then you'll see both layers together for each image. You can make manual measurements if you wanted. Let's say, let me just look at outline so I know what layer I'm in. Let me go to my secondary, and let's say for whatever reason you didn't want this one included. So we'll just hit our select tool and double click it and erase. And now that that edit is temporary until you choose to either save that edit into the current black and white image, which will overwrite what the recipe output with this version, or you can save as and give it a new name, _edited or whatever, so you have different versions of your fully automated versus semi-automated, or you can undo it. And then you've of course got tools for selecting, freehand selecting missing features. Hypothetically, let's say this is a missing one. Select that and say fill, and that gets added to that image. You can select multiple features. Click, click, and then double click the last one, or click, 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 and press enter. Erase those. Pen tools for drawing lines in between things. So ways of going through, let's say I hit save now. Now edits are saved, and now again my slider is active, so I can move to other images. You can double click on any image to go to it and its counterpart. So I could have double clicked to get to a different image, and it just would have warned me that you need to save your changes in order to advance. So the slider is inactive, but I can still type in a value to go to a different image, and it'll just tell me if you advance without clicking save, your changes will be lost. So what do you want to do? So once you're happy with your segmentations and you're in the layer that you want to measure, of course you can make your global measurements directly in here. So we could just say measure area fraction. And now that'll measure the area fraction from all of my secondary segmented images. And I could do the same to the tertiary to get their measurements. Generate like that. And then again, if you wanted, let's say, particle size, so we had our secondary shown, we say measure equivalent diameter . Now we'll get a couple of things. We'll get one big spreadsheet that has all of the features measured per image. So here's the first image, all of its particles. Here's the second image, all of its particles. But sometimes what you're after is just the average particle diameter of every image, and you don't want to go through in Excel and make a different spreadsheet that averages each of these columns. So we also export a means file that has the average equivalent diameter per image, which is just gathered from this other spreadsheet. It's just taking the average of each section. And there's been some requests to add like min, max, and standard deviation to this means spreadsheet. So that should be in the full Beta 7 release in mid-July. That is how you would work through batch processing a set of images with a recipe and checking it out, making edits, and then making measurements at the end. About a half hour in, that's probably a good overview of the different applications. The real-time processor I didn't go into, obviously. That looks just like the batch processor and it has all the same functions. Its only difference is that instead of giving the app a set of images ahead of time to process, say, post-acquisition, this can monitor a folder, and every time a new image is added to a folder, then it will execute the recipe on that image. So sometimes we have data sets that are being collected and the files are saved to a data center. We don't use this much, but sometimes it is helpful to have the images being processed as they're being acquired. So while the next one's being taken, the previous one's being segmented. But that's probably our least used application. Any questions at this point? Okay. So we can move into more of the details here. I have the subjects organized by folder. We went through our overview. There was requests for just general segmentation. Let me just check my records here. Let me go bring up the participants. I think Trevor had asked to see segmentation, but he might be with us on the Thursday session. And Daniel, and I believe his colleague, I'm going to not pronounce this correctly, but Yashin Chen is joining us. He had asked to see segmentation of difficult structures. So why don't I just go through a few examples from different areas. I've got some bio ones. I've got some materials or metals examples, and then a composite example. And we can just see a few different recipes in action. And please ask any questions along the way.
Hey, John.
Yeah.
Sorry to interrupt.
Oh, please do.
It seems like a lot of these image analysis features are tailored towards fairly, let's say, homogeneous type microstructures where you have features kind of everywhere in the image.
Mm-hmm.
I am someone who does a lot of coatings characterization where, variations between layers are fairly substantial. And we have coatings multiple layers. Usually thresholding for one will kill it for another.
Right.
And we are looking for directionally varying features as well. Doing gamma prime is it's a really good feature to have, but, in terms of looking at a thermal barrier coating for aerospace application, is there any specific tool set in here that would be tailored to coatings like that?
I think so, definitely. Let me open up this kind of strange how different fields of study can have analogous type images that are called something entirely different. So here I have an image of a wound, I believe, in a human that is healing, and I think this empty space here is the remaining wound. So the recipe that we came up with to find this center area was a threshold and then some dilation steps, or some morphology steps, I should say. So let's let that go. So we started with a threshold and then went into some cleaning steps and then ended up with our wound area and the healing portion. So if you wanted to find these fine features in this wound, let's say, but not anywhere else in the image, and you treated this as sort of a multi-layer structure, then what I would do is set up a few steps like I've done here to find a sub-area of the image and put this in a memory slot. Put it, I guess, let's say restore image 1. And I don't need this here because I'm going to rename this layer and just call it area of interest. Okay, so now that area of interest is in that memory slot. And then we'll bring back the original image. And I would go into one of my threshold tools, like the adaptive threshold, where if I just ran it on the entire image, I do a window size of 20, just because these are pretty fine features. 20 pixels kind of nicely spans them. And I like to start off with a percentage of 100 and then adjust it from there. So if I'm after those fine features, but I don't want to find anything in areas that are outside of my AOI, then I would just from the mask pick any of the memory images that I have stored that are black and white memory images, which the restore image 1 is. So if I just pick that now, I'm confining my thresholding to that auto-determined area of interest. And then what you would need to do, since again your selected features need to be black, if I just went and took this image here and inverted it and put this in this most important memory slot, the companion image. Now if I did a keep lighter operation, that would take all the lighter pixels, in this case white, between the current image and the latest companion image. So I need to first bring back my restore, which is this one here, and now I'll do a keep lighter between the current image, which is this one, and the latest companion, which is this one. So keep lighter pixels will fuse the two of them together. And what I would like to do first is dilate this a little bit. And then get rid of those small white features. (26 pixels). And then erode everything back down by the same amount. This one now has to be your companion. We can get rid of this one. Now we'll take this one, we will add it to this, and to avoid getting those residual bits at the edges, I can just shrink this down a bit to confine my area of interest closer to where my features are. I probably want to do a very small noise clean and say anything that's under 20 pixels, get rid of. So then there I've only found the larger features that are in that portion of the image. So I definitely think that an approach like that could work. You just have a couple of steps to find your different layers, and you can then perform different image processing operations inside of each one to get what you're after. Is that helpful?
Yeah, it's very helpful, John. Thank you.
No problem. So that was the first one that I was going to show anyway, the wound healing recipe. Let me just load that back in as it was originally. And we'll just explain what it's doing here. Since this has an optimization step already in it, this is probably a good opportunity to talk about what that means. So again, what this recipe did is it first went with an adaptive threshold, which is probably our most commonly used threshold, instead of a conventional global value, which just picks a somewhat arbitrary threshold value to select pixels on either side of it. This goes in and looks at every pixel locally, one at a time. So it would go into this pixel here and say that if you consider a 20 by 20 pixel neighborhood around it, so a square that's that by that, take the average gray value in that window, and then if that center pixel is more than 103% of the average of its window, then it gets made white. And if it's less than 103%, it gets made black. And you can also operate in departure mode, which says that a pixel has to be 5 units or more greater than the mean that surrounds it in order to be selected white, otherwise it's black. So it's a way of selecting pixels based on how bright or dark they are relative to their local surroundings, instead of relative to just some scalar cutoff pixel value. So we use that quite a bit. So that kind of found, a lot of white pixels here in these healed areas, and then it was clear that we could just do a little bit of noise cleanup of the white pixels and then erode the image by quite a bit, where we broke up these white features or agglomerated them together to start defining wound versus healed regions. Then we just had to go and reject small white features that were remaining, do the same for the black features. And then this last step would be important to get right, this redilation step, if you're trying to accurately measure, say, the area fraction of the wound, since if I unoptimize this, so we can see what its effect on the area fraction would be right now. Do area fraction here. So the area fraction of the wound is 52%, but if we, and let's look at the outline, seems reasonable. If we just changed our, what are we at here, 53%, if we changed our dilation by just 2 pixel values, that still could be considered, I guess, the boundary of the wound, but now we're measuring 53.5%. And if we went further, do 2 more pixels, now you're at 54%. So which one is right, I don't know without any sort of objective metric to fall back on, which is why we have this optimize tool. If we have a particular step and we say optimize it, we're going to now compare the similarity between the segmented image, which is, let me show the black and white, which is this one. I'm going to compare this image to some comparison image. I'm just going to use the original here. And we're going to use the full image to do this, and we can choose our comparison metric. I either do mutual information or intra-class variance, which are two different image similarity metrics. Sometimes you need to try out both, and because sometimes one can be way off the mark. If I chose mutual information, now instead of having to decide on an exact depth value, I'm asked for a range to explore. So I can try anywhere from 0 to, let's say, 20 in steps of 1. Now it's going to try out that tool at each of those depth settings and compare the segmentation to the comparison to the original image, and you're getting an image similarity value here. So then it says, aha, at a depth of 8, we maximize our similarity between segmentation and original. So now that's what I'm going to choose as my dilation value. So you at least have a quantitative and defendable reason for choosing 8 instead of 7 or 9. So that is optimizing the step. And that also then lets, again, just like with choosing auto for a global value threshold, if a step is optimized, when this recipe is rerun on a new image, that optimization calculation gets reperformed so that maybe the next image, if there's some variation for whatever reason in the imaging conditions, you might come up with a different dilation depth for the next image. So it lets the recipe change on the fly and be more flexible. Here is another image that is a pretty nice example of something that looks easy, but ended up not being so easy. This is a slice of some dendritic material. I think it's a bulk metallic glass with crystalline dendrites in it. And your first inclination might be to just go with a global threshold, because those things look way darker than the background. Slide this up and, okay, we've got a gradient, I guess. That's not going to work. So we could flatten the gradient. All of your grayscale manipulation steps are under the pre-processing menu. So let's try to flatten the background. And it's better. So then from here you should just be able to do some cleanup to get rid of the rest of the noise. We would add a classic dilation step, which would fill in the missing black pixels here. Usually start with 6, and then if you need it to be more aggressive, you can go down. This is saying change a pixel from white to black if it's surrounded by 5 or more. If out of its 8 nearest neighbors, 5 or more are black, then make it black. If you go to 6, now 6 out of the 8 need to be black. So it's less aggressive. 4 usually is a little too much because it starts to grow boundaries instead of just cleaning up noise. And then we do the same for the black ones here. Maybe go to 5. I did a classic erosion. And then we can get rid of these tiny ones, of course, easily with a reject features. Measure this one in 17 pixels, so I think 100 is very safe. And we got this last little streak here. We can revisit this image when we go into the FFT processing. These are some imaging. This is actually part of a 3D data set. So these are artifacts from the slicing operation. With an FFT filter, we can minimize these streaks and avoid this artifact before it even has a chance to show. So this isn't bad. However, if you really need high accuracy to your segmentation, then you'd really want this to be continuous. You wouldn't want this joint here. But we can't go after this with a watershed, even though that would successfully separate this connection here. If I went with 2 and 2, that would get cut. Let me go a little weaker. But now this also gets cut, and this needs to be completed, as does this one. So this is a pretty tricky microstructure where you can't rely on your watershed to fix your mistakes. So we did try, instead of a global threshold, going with a adaptive. Let's insert that one below. And we struggled with it for quite some time because we really needed a real fine window in order to capture that separation. But we were then left with a lot of this other noise in the matrix that, if we go up in window size, some of that noise goes away, but now it's tougher to keep that separation intact here. So we wanted to go with a small window size to nail that, but then ended up with a lot of this other noise that was tough to clean up. So here is the recipe we settled on. It's way more steps than the first one. So if the first one works for you, then by all means, go quickly into my preferences and just turn this off. So, okay, here's the FFT filter I was talking about that reduced the curtains somewhat. Went to a flattened background. Now at any point you can, I should have mentioned, this reference image doesn't have to stay fixed. If you wanted at the very end to be outlining your segmentation on something that was better than the original, you can just go to any image in the recipe and right click on it and say set as reference. So now that becomes your reference. So we did our adaptive threshold. We found, the boundary was intact, was separated, but we had a lot of this other noise. What we did to get rid of it is some logical operations. So we first cleaned up some noise, and this actually was used to kind of agglomerate a lot of the noise together, and you'll see why in a second. And we put that away to bring back later, and we recalled our processed grayscale image here right after the background flattening. And we ran a normalizing contrast step on it. We did now a coarser adaptive threshold that tried to only find some of the pixels inside of the dendrites and nothing in the matrix. So we cleaned up a little bit, shrunk down. Now we treated these as seeds. So we said, and we know these aren't the complete dendrites, but these are going to be markers for us. And then I think I got rid of a couple extra noises here. So now we're going to set these seeds as the companion image, and we're going to go back to this state in the recipe. So we took our companion, we went back to this state, and now we said keep mutual features, which is saying take all of the features that are in this image and keep the ones that contact features in the latest companion image. So we go from this to this, which gets rid of all of our matrix noise. And then with a couple other steps, we fill in the remaining noise. And it looks like I didn't quite keep my separation intact, which is a shame, but I can adjust that a little bit. So it's quite a bit sensitive around this parameter space. I thought at one point I had successfully done that. Let me I think the issue is with some of these steps. If instead of before that, if we get rid of some of that noise here at the interface with a classic erosion of six and 1, and then this comes in. We didn't get it perfect, I guess, at the end. I know I had this tuned at some point where we did have that completion, but I don't want to take too much more time with this. Those are two different approaches, I guess. Neither one of them is perfect. One of them saves more of the boundary, but has this issue here that could, of course, easily be manually corrected. But if you're trying to go after this fully automated as like part of a 3D data set, then you wouldn't want to avoid having to do this. So that's a couple of recipe approaches for this one image. One uses adaptive thresholding and then grabs seeds and keeps the features within the seeds, and then tries to get rid of the noise. And I do think we can get this a little bit better. And then the first approach was much more basic and just went with a global threshold after a background flattening, which also worked, but was less effective at keeping the separation. So we're 1 hour in here, and we've gone over an overview and then some different segmentation problems. I'll put one last one up here that will be pretty quick. It's a composite with 2 different particle sizes. It's actually an image of asphalt. And this approach here went in and separated the fine and the small particles into different layers. So at the end here we have a coarse and a fine. And instead of just clicking through the steps again here, why don't I try to build hopefully a little shorter recipe from scratch, and then we can see some different thought processes. What I would probably start with is finding the bigger ones first. Let's see what a global threshold looks like. A little bit of a gradient in the image. So let's flatten that first. And then we'll try a threshold here. And then I would do one of my classic erosion steps. And then maybe erode the features ever so slightly. Just to get rid of some of the noise that touches the edges. And then we do a small black feature rejection. Reject everything 150 pixels. Now I can dilate back, and looks like maybe we should have chosen a higher value, so let's go edit the reject features. How big is that? 300. Okay, so maybe we need to do 400 pixels. Now those are gone, we've redilated. And now I would dilate a little bit further to break up some of the smaller ones. So we're going to change this, do something like that. And now I have to decide what I want to call coarse versus fine. You could make, I mean, you could decide, you wouldn't have to decide ultimately what you want to choose as coarse or fine, but you probably would want to choose which size features are best found with this basic global threshold approach and get rid of everything else. So I'm going to say that everything under this size I'm going to get rid of for now. Let me say get rid of everything that's less than or equal to 500 pixels, white features. And now I'm going to put that as my companion image so I can use it later. And I want to bring back my flattened background state, so I just need to set that as a memory image. So let me set that as restore image 1. Go to the end, bring it back. And now let's go with a adaptive threshold to get the fine ones. Let's try 20 and 100. Here's where we could use an optimization to try to find the parameters in the fine area. So why don't I do that? Why don't I say that I'm pretty happy with a window size of 20, just based on the feature size here, 20 or 30. But I want Mipar to tell me what this percentage value is, because that can make a big difference. So in this case, we'll say optimize this step against the prior image. That's fine. That's the restore image 1. So prior image or restore image 1 would be the same thing in this case. And this time I want to use a sub area. And I'll again use mutual information. So now it prompts me to draw an area on the image, and then double click the edge of it to confirm. I'll keep the window size fixed, and I'll let the threshold vary from 90 to 120 in steps of 1. And now it's saying at 99 I hit a maximum. So that's what I'll choose as my threshold value. Now I'm not going to keep this step optimized. I just wanted to use it once to sort of train the threshold step and choose what the values should be, but I want to use these same values for the next images that I work with. And now what I need to do is, if I wanted to get all of my particles together without any sorting, I just wanted all precipitates nicely segmented, I would take my adaptive threshold here and run a cleanup on it, which is just kind of a standard approach that we always take. Now between this image and the companion, I'll do a keep lighter pixels to bring the large ones that I nicely found and merge them with this image, and then do an invert so that my particles are selected. And now that's my end result. And I missed a lot of these small ones, so maybe I wanted to use a 6 instead of a 5 here. There we go. Now if I look at my labels here, I can see there are a lot of agglomerations. Maybe not. Not as many as I thought. Some of these, this should be separated into 3. It's not clear. You probably need higher resolution at this fine scale to be confident about it. I could run a watershed on everything here and just make sure that it doesn't. We could do what we did last time. We could keep the larger ones so that we could add them back after the watershed if we don't want to erroneously separate any of them. But let me just see what the weakness of 3 does. Have to go down to 1 to get the small ones to separate. Yeah, now you do cut up some of these larger ones. So we could do this. We could go and say, let's reject everything under 500 again. Put that away. This full, maybe a little bit bigger. Let's only reject everything under 200 because some of those things there are. Oh, I'm sorry. No, the other direction. We're just trying to keep the big ones so they avoid being separated. So they're the big ones. Put this in memory. Let me go back to this state because I need to set this up as an image so I can bring it back later. Oh, not there. After the invert. And now I have my larger features. We're going to now recall this state and run our watersheding on everything with a very strong setting. Not that strong. Dive in here. The weaker you make this, the fewer lines should be drawn. But for see, there's some very strange things that happen to very small features at too large of weakness values. So I might have to settle on 1 there. And now I can do a keep darker between this and the companion to bring back my preserved larger features. Okay, so now I've got all of my features here. If I wanted to sort these at this point, then we can do that. We can say that anything, maybe this feature I want to call. And actually, I think some of these, a problem like this could have been prevented by, before we start with all of that water shedding mess. I'm just going to run one last noise cleanup here to get rid of some of those white features. We'll do a classic dilate of 5 and 10. How about a white feature rejection? Now at the very end we've got separated fine particles. Make this even stronger. So we can now take this state and say, set this in memory. Let's reject everything under this size and call it fine. So 539, okay, 500 is a decent selection. Get rid of everything under 500. And now go invert this and do a keep lighter, which will subtract these out of our companion image. Now we just have the others. So we went, here's all of our precipitates, set that up as companion, get rid of the smaller ones, invert that, and then merge lighter between that and the companion to give us this. So now we can set up a few layers if we wanted. We could say this step found all of the precipitates. So I can just do a set as layer. I'll make this blue. And we'll say these are all precipitates. And this one is coarse. And this last one is fine. Make that red. Now I can look at my layers, and you'll get all three of them overlaid. But now in the latest release, you can hide certain layers. So I can hide that one and just show the fine and the coarse, or hide those two and show the coarse, or show, sorry, all precipitates. So, you know, for certain problems, it could take you a little bit of time to build up the right recipe, or we're always happy to receive an image and send back a custom recipe. But once you have this now, go ahead and save it and use it again and again on all your images. It takes far less time to where that recipe got saved. It's in there. Oh, that was right. Open and reload. It takes far less time usually to reload a recipe on a new image than it did to build it. So once you've got your recipes for your different problems and you're building up your library, you should be pretty well set with accelerated image analysis. I think that's definitely a good coverage of some different segmentation approaches. Anyone have any questions or comments on any of their segmentation problems that they would like to see covered? Okay. There are a couple other examples I could go through. There we also have our recipe store that hopefully a number of you have browsed. I think everyone, if you've used Mipar at all, should be pretty familiar with it. We want to add more to it as soon as we can. But we have a number of recipes organized into different categories. There are metal recipes, biological ones for cell finding and bacteria colony finding, cell identification. There's our wound. And some ones for, there's our asphalt, core shell particles, different reinforcement in matrix. The more challenging ones, and then a few miscellaneous ones. I don't know how many of these will be helpful to you, but we have done work in all kinds of different areas. Even got some from finding burnt cheese on pizza. Might throw that one up there too. And then at the bottom, of course, always available is a custom recipe order. Put in your image, tell us what features you need, and we'll try to get you one back as soon as we can. So I also had on the agenda some pattern mapping coverage. This won't take too much time. I'm not sure. We've got Brian Martin, I believe, from Iowa State is joining us. Matt, Kenny, I also see you here from Iowa State. I know you guys are working with some titanium microstructures where you have different alpha colony orientations that cannot be segmented by intensity, but need to be segmented by pattern. Let me show you what I mean here. Here's an SEM image of some colonies in titanium where we'd like to identify all features that are going in this direction as one colony, and maybe this as another one, and this as a third one. So we do have a pattern mapping tool here in Mipar that was actually developed for this exact kind of problem. It's definitely a little slower to run than some of the intensity tools, so we can show you some tips here. This image is you see about 600 by 400 pixels, which is right in the wheelhouse for where you'd want your pattern mapping tool to run. Anything bigger than 800 by 600, and you're gonna be sitting there for a few minutes to let it run. But in all honesty, the pattern mapping tool doesn't need that many pixels to work with, and in some cases performs better with downsampled images. So I think you could even take this image here and resize it down to 300 by whatever kept it the same aspect ratio, and possibly even get some good pattern mapping results on this, because all it's needing to find is some local directionality in your microstructure, which I think it would still be able to do with this resampled image. Let's take a look and see. So after I've resized, I can go from my feature finding menu right into pattern mapping. And now we see a number of fun toys. So we've got a few approaches to pattern mapping. We can either map out different properties of a pixel window's what's called a two-point correlation function, which is the approach we'll take here. We can also map different intensity sums from different local windows FFTs. For example, if we just wanted to find features that were running in this direction, the easiest way might be to go in and let me look at a 40 by 40 pixel FFT around this pixel here just to define my mask. That is not too helpful. Sometimes you have to go and take a bigger window size to define your mask. Let me set up. So this streaking here actually indicates that there are a number of features that are oriented perpendicular to this direction. So I should be able to, I'm sorry, I forgot you can't rotate the ellipse tool. Well, that would be handy in this case. Let's make an outline here. I just chose that part of the FFT. Then I'll actually use a window size of 40 to do my mapping. Section grid will split up this image into a 5 by 5 grid of, in this case, 5 by 5 grid of sub-images, and each pixel within each window gets processed in parallel with the others in that sub-area, but then each sub-area gets processed in series. And this is just a feature to avoid some memory errors, but it really doesn't add any overhead running those windows in series like that. So in other words, doing all pixels in the entire image in parallel isn't much faster than running the image in those tiles serially. I usually will just put in 3 for the section grid, and let's then calculate and just see what comes out. So the first time you run this, you start up what's called a parallel pool, which just aggregates your CPU resources together. Those parallel pools, I think, stick around for 30 minutes. So the first time you run it, you'll need to wait a few seconds here for that pool to start, but you shouldn't have to wait again for another 30 minutes or so. Let's just let that get going here. Sorry for the wait. I'm not sure what the problem is here. Maybe there is an issue there. Let's try this one instead. Okay, so there must be an issue with the FFT mapping. We will check on that and get that fixed before the full beta 7 is out. What I did there is use the 2-point correlation, which is better suited for this particular problem anyway. Let me quickly show the FFT matching, and then we'll go back into what that just produced. So the FFT matching lets you choose different structures and then color the image based on which structure that local area matched the best. So if I use a 40 pixel window size to define my different fingerprints, so to speak, I would say choose references, and I would say, okay, that's one fingerprint, that is another, that's another, and that's the last one. So 4 different, in this case, calculate. So now this is taking every pixel and comparing its local pattern to each of the 4 patterns that I just defined. And then it will color every pixel one of 4 colors based on which of the 4 fingerprints it best matched. This can be useful for high-resolution TEM images. It worked okay here, but not great. You can play with your window size and maybe choose different references, but that's probably not the best approach for this kind of image where you're just trying to separate different patterns based on their local direction. I can show that FFT matching on a high-res image here in a second, because I think that is better suited for that kind of work. For this image, let me switch to 2-point correlation and go down to a 30 pixel window size, because 30 pixels, how big is that? You want to balance and you want to have enough information in your windows so that you can accurately judge the local pattern. But that's a little too big. I think we could go down to even a 15 pixel window size and have enough information, but then also keep spatial resolution. So now this is the angle of the 2-point correlation function mapped on a color scale. That's the eccentricity of it, that's the radius of it, and that's the thickness of it. Contact me if you're interested in learning more about what the 2-point correlation function is and how it's used. If we look at the angle overlaid here, we have started to segment now the different orientations. So the blue, its angle is sitting at about -20, and we've got some other artifacts here and there. I can try upping the window size to 20, and let's see if some of those artifacts go away a little better. And now I can group pixels together to make features in the binning here. We could do a bin size approach where we say every 20 degrees we group those angles into a bin. And now we could run cleaning on this to say, take features that are under 200 pixels and change them to the color that surrounds them. It's definitely not perfect. We've got problems around the edges. This swath of glass did not get nicely found. We can go back to any of these pre-steps and see where the problem might be. Let's try a slightly bigger window size. I think there's some issues with the edges here. Very small one and see what that does. That's pretty messy. I had to go and pick one of the tougher images to demo this on, but this is the kind of workflow that you want to work through. Finding the window size that best suits your microstructure, and then playing around with how you turn this continuum of angles into features. Instead of bin size, you can say, I want only 5 bins in my image. Or you could say the watershed approach, which helps try to flood fill this image into separate features. And that's going to depend on this window size that you pick. The window size goes and first makes a gradient map of the image to try to find where there are sharp changes in angle in the image. So the default setting is close to the window size that you use to make the map, but I usually drop this down to something lower, and then the weakness, just like before, controls how many features remain. So you can try out different settings. This is obviously not great. You can lower both of these a little bit. So I need to play around with this image a little bit more to get parameters that worked. But the tool is here, and for some problems this is pretty invaluable. Let me bring up one of the submitted images that I believe Brian submitted. He's working on trying to get these colonies sorted out. That's definitely a tough little problem there. I'd probably definitely resize this first of all for your, especially for your experimentation. Let's take it down to 800 and see if that gives us anything to work with, or crop the image. You could also do that to just work on an area. Let's do that instead. Just play around in this region for now. Let's try 30 and 5. In this case, we're again trying to sort out different regions of different feature orientation. Now this could be a case where instead of trying to measure colony size, trying to measure the size of these group colonies, you might be after identifying whether this is a so-called colony image or a basket weave one in titanium metallurgy. There's the pattern map where we do have different local orientations captured pretty nicely. And we could go in with a watershed here and try to group all of these angles into features. I'm going to enter some things here and see what happens. That's not bad. And then the last step here is to decide how you want to I'll turn this into a binary image. Here you'd probably say segment bins with a thickness of 1 in between all the pixels. And then this would draw lines along all of these bins here. It's troubling. This looks good, but this has a slightly different angle shade than this one, so we might need to increase this weakness a little bit. And now go to our segmentation. And then if you hit accept, then this is what's output from the pattern map. So instead of going after trying to group these into angles, we could do, and I know Matt and Brian, I think this is something I've talked with Thomas about, trying to quantify the degree of colonization of an image like this. Instead of mapping out the angle, we can map out the eccentricity. And what this is, so your 2-point correlation function, if you take a look, and I'll again be happy to talk with you more about it, it's going to be going to have a hot spot in the center of it that is more eccentric for very directional areas of microstructure, and is very round for less directional areas of microstructure. So the higher the eccentricity value, the more directional that little bit of microstructure was. So you get pretty high values in here, and at colony boundaries, like right here, where your window is going to encompass a few different orientations, this local microstructure isn't so directional, so its eccentricity is a little bit lower, down at 0.7. So you could, off of just this eccentricity map, define a threshold that defines colony versus non-colony, and say that, let me pick 0.7 and above to define, let's do 0.8 and above to define my colonized areas, and everything else is going to be either basket weave or unknown. Let's make this red. Now these would be my areas of microstructure that I deem to be very directional. Everything else is not so directional, and it does make some sense here. So now you could measure the area fraction of all of the red and say that 72% of your microstructure is colony. But you just have to come up with probably some standard samples to calibrate some of these parameters against the sample that you'd call 100% colony, and a sample that you might call 0% colony, and just make sure that your pattern mapping parameters match up with those calibration samples. And hopefully for some of the others on here that aren't working in titanium, not sure if Thomas is with us. Maybe he's joining us. Thomas from Alcoa, he might be joining us on Thursday. I think he's working with some directional microstructures like this. I'm not sure either if, I think the other gentleman has left us who was asking about thermal barrier coatings before. But if he sees a recording of this, maybe these tools are helpful for him. So that's some pattern mapping. We're an hour and 40 minutes in. And I think, yeah, let me not forget, Johan had asked, he's from Port Elizabeth, South Africa. He had asked to look at some high-res TEM images with the pattern mapping tool to help map out the different phases from atomic columns. I do believe I've got an image that could work for us here, if that ever opens. Yeah. So if we had, let me open that one up. my FFT section, but we can work with it here. If you had an image like this with an interface between two different atomic structures, so here we have HCP titanium, sort of a hexagonal arrangement to these atoms, and a body-centered cubic structure. You first might want to filter this image, although I think the technique can work. It has worked for us on raw images. If we first ran an FFT filter, all of these spots indicate high-ordered positions in the image. So we could go in and use our circle click tool and pick off these spots. They keep those and then mirror over the origin. All right, take care, Brian. Now that would be a filtered image that I'm going to work with. Just kind of got rid of some of the background noise. And if I take this image into my pattern mapping, I'm going to use 40 pixels maybe. Here now I'll use my FFT matching tool, where I'll say choose references, and I'll pick 1 pixel in here and 1 pixel in here, and then say calculate. So the hope is that I end up with most of the pixels on this side of the image labeled as one value and on the other side as another value. You've got a multi-core workstation, and this should run even faster. We've got 8 fairly old Xeon CPU cores in this workstation, and this is a parallel CPU loop that's being run. So even virtual workstations these days with 12 virtual CPUs have outperformed this physical workstation. And Johan, yeah, you asked how do we choose the 40 window size. A little bit of experimentation. You saw me first use the distance line tool to just kind of see what amount of microstructure or what amount of image content would be contained in 40 pixels. Wait for this to finish and that'll, okay, it pops up there. So 40 pixels is, just my grayscale image here, 40 pixels is about like that, so that kind of spans 1 unit cell almost, but you can try running it at 30 or 50 and just see which result looks better. The result here, zoom all the way back out, and I'm sorry, I don't know why that blue feature is made transparent, but that is that's the raw result right there. So it's pretty good. We just need to run one cleanup on it here. I would do an all noise removal here, maybe with a 4 and a 10. Let's undo that. Let's first go and run this on the first bin. Let's run it on the second bin first. For just an image with two phases like this, you could just choose to do all of your cleaning after the fact. That's what I'm going to do. I'm going to take and just keep my, I'm going to threshold on this and just keep the second bin here in black. Yeah, Johan, 1 unit cell would be ideal if that gives you enough information. I think we'd probably get a little better pattern map if there was a few unit cells in the window. So off of this threshold here, I'm just going to dilate everything a little bit. And then reject all features. And then dilate some more. Reject remaining white features. And then erode back by what I dilated. So I dilated a total of 10. So if I erode by 10, now this you can call your interface between HCP and BCC. And it, in this case, worked pretty well. Or if you wanted to set up a layer, of course, a couple of layers, just take this and invert it, and then call this side HCP. And this side BCC. If you wanted nice smooth boundary across here, even though I don't know that that would be physically accurate, you could take, after your erosion everything, and you could replace that black feature with its convex hull, which would draw a straight line to smooth out all those boundaries, but then you end up with something that's probably not quite as accurate. It doesn't capture some of the fine modulations on at the interface. That is up to you. Okay, so that's definitely that's pattern mapping. Those are some of the harder segmentation problems you'll encounter, but there are some tools there to help get at least partially through them. We would next move on to maybe measuring precipitate thickness. I also have here the remaining topics I had requested: precipitate thickness, particle size distribution, phase fraction, FFT filtering, and then finally stacking 2D into 3D. Is there anyone here that is using Mipar for 3D analysis? I think maybe Yashin is. Johan is as well. Okay. So we can hit 3D at the end. I've got a data set we can look at. But let me get through some of the other 2D topics. But I think we've already covered measuring phase fraction. In the overview, I know we talked about, it really comes down, your measuring phase fraction is going to come down to how do you segment the phases, and then how do we measure the phases. Okay, yes, Sean, absolutely. Thanks for reminding me. I did want to show your, is it okay if I use your gloss images to demo? Okay, that's perfect then. I will do that. Sean here is working on trying to use image analysis to quantify the glossiness of the different paint specimens.
Yes, actually, different printed and embossed segments.
Okay. So, yeah, why don't we then treat the phase fraction section as just some other types of global measurements that you can extract from images, and I think we've come up with a recipe that can be used to quantify glossiness, so we'll cover that there. Precipitate thickness. So is there anyone on that is interested in that? This is mostly from folks that are working on those alpha lap type microstructures. Okay. Doesn't seem like there's too much interest in that, so why don't we skip over that, and maybe some of those folks are planning on joining us on Thursday. I've been in contact with a few of them. Particle size distribution, we definitely covered. I think I showed in the very beginning. Let me touch on that really quickly again. Let's just go back to our composite SEM image that we had and load in the recipe that we found to find the particles. Now if you just want to measure the, let me switch to a color map instead of a single color. So there are your particles just colored randomly based on their being separate. And if we wanted to measure the distribution, then we would just need to make the measurements. And maybe you were after the area of every particle, or maybe you're after the equivalent diameter, which is the for every particle, the diameter of the circle that has the same area as the particle. We can also do the minor axis length, the major axis length. We'll be adding the farad diameter, since I know that's a common metric. That's really the largest chord length that is seen in the image. We will try to add that by beta 7. We can also use our intercepts here to run 100 lines through the centroid of every feature and take the average of those lengths as the diameter of the particle. Because when you move away from spherical particles, circular particles, the term diameter or the term size is a little bit harder to define, so it really depends on what you're after. Equivalent diameter is usually a pretty standard measurement of size. Because you're still, at the end of the day, you're reducing a complex feature into a more ideal measurement like size. So you're having to make some assumptions or set up some constraints at some point along the measuring. If we wanted to get an equivalent diameter distribution, then we set up our measurement file and we generate the measurements. Now there are no plotting tools in Mipar yet, so you would need to rely on your favorite plotting software, let's say Excel, which is still not the greatest for making histograms, in my opinion, but I know a number of folks use it. So here we have our column of diameters, one for each feature. And I believe I have I thought I had put the analysis tool pack on here. I'm not sure where to access it here. I don't want to make this a tutorial about using Excel, but you've got your data to make histograms out of here, of course, a diameter for each particle. And then we showed, of course, before, if you want to visualize the particles by size, no need to regenerate. We already have that text file made, so we're just going to load that in and then use this data to colorize your particles. Krishna asked, yes, do we have examples where we have more agglomerated particles that are not so well defined? And we definitely do. Let me find an example here real quickly for you. This could be a decent example. Does that look reasonable to you, Krishna? Let me just show what we did for that case. Johan asked if we have any examples where we overlay images from different signals, SEM and EBSD data. I don't have any of those handy with me, so let's definitely chat offline, Johan, about doing that. 'Cause we haven't done that too often, but we do it sometimes, registering one against the other. Where's my example? So the recipe in this case looked like this. So we went with a watershed and then feature rejection approach, because there really isn't, it was tough with a thresholding to get nice continuous outlines around all of these particles. So we first inverted the image and then ran a watershed directly on the grayscale image, where these highlights, now these bright highlights, are interpreted by the watershed kind of as stopping points. But the quality of this watershed is dependent, of course, on its weakness setting. So we went and we optimized that weakness setting against the inverted image with that mutual information calculation as before. If we unoptimize it, I can just show you the dependence here. So if you're down at 30, you get more separations. And as you go up and up, up, you get fewer. So we ran the optimization. We said use the prior images comparison. Let me just work with a subregion for expediency. And I tried everywhere from 30 to 60 in steps of 2 to 5. And I was trying out that separation at each value, and it comes back and says 55 is optimal. Now, I think if I refined my, let's try from 40 to 60 now, and let's do steps of 1. We did miss that one particle. 56. Still not there. But we didn't include that area in the consideration, so let's redo it with the entire image. And we'll coarsen the step size. You're, of course, welcome to just manually select the weakness value, since you might have to in this case, but once we consider the full image, now the optimal value of 50 looks better. But we're just left with outlines around the features. We still need to discriminate, inside the particle from outside. And I know this wouldn't always be the case if you've got particles with nice intensity contrast between precipitate and matrix. So I don't want to drill down in too much detail on this example because it's mostly just going after agglomerated particles. Krishna, if you have, I know you had sent me a couple of slides a while back with your images, but I didn't want to include them. I'm not sure if I'm allowed to do that. But I'd be happy to work with any raw images that you have, because it's really just going to come down to the recipe that we need to make for your case. It could be very simple and just require the right adaptive threshold with some cleanup and then water shedding to separate the features. But we can certainly handle agglomerated particles depending on what they look like in the image. So it's a case-by-case kind of thing. We first got rid of big features, very, very large features in this image that are clearly background. And then we went and kept very eccentric features that didn't have many perturbations coming off of them like this one, and we kept those because we know these are likely going to be bits of particle that need to be preserved. And then we went back to this state and we got rid of, so convex area to area can be a helpful measurement for discriminating, in this case, between matrix and precipitate. If I go into the tool and we're looking at this particular parameter to isolate features by, and I unpreview the result, if I go on and measure, say, this feature versus this feature, the red one here has a much higher convex area to area ratio than the orange. Convex area to area takes and encloses the feature in the tightest fitting convex hull that is possible, and then takes the ratio of that area to the features area. So features that have arms and things shooting off them, a lot of concavities in the surface, will have a high metric, and more round, smooth features will have a lower value. So it turned out in this case 1.25 nicely separated these remaining matrix features from the precipitates. And then we ended up with this. And now there were a couple of eccentric features that got eliminated, but we had saved those ahead of time. Back here. Looks like we did save a piece of matrix erroneously, but we were okay with that. and then just a dilation at the end, which you can optimize to make sure that you need to dilate. We look against the original image here. We try dilating from 0 to 5 in steps of a half. And Mipar comes back and says, not what we wanted to see. Here's an example where optimization can not quite give you what you want. Sometimes we can play and we can filter the image ahead of time and give Mipar something other than the original to compare against. That's probably what you would need to do here. In this case, we just used a dilation of 1, since we felt these outlines were a little bit under the actual outline. So yes, here's a case where you did have agglomerated features that did get separated. If there is no visible boundary between the particles, but you know that they need to be separated, then that's usually where your watershed tool can help you out and separate two touching particles that there's no boundary defined with a threshold. Is that helpful at all, Krishna? I know this example probably doesn't really apply to you. I think the images you showed had a little more contrast between particles and matrix, which, if anything, should make it easier. Okay. So yeah, let's move on here to go back to my webinar. Let's move on to looking at some of those glossy images, and this will just be a discussion on ways that you can manipulate intensity images and get some global measurements about them, something other than phase fraction. So if I have Sean's images handy, let me just go and grab those. Okay. So here are the images that you provided, Sean. We have the glossy one here. And then the non-glossy. So my first thought was that there's definitely something visually different about them. And what is the best measurement to capture that difference? What I came up with, if we take this, yeah, no worries, Johan. Thank you very much for for attending. I know it's late where you are. We take our non-glossy image and we can run the recipe that I made. So all I did is I took and I first flattened out the background. I went from this over here to this, just so that we didn't have any gradients that were influencing our measurement. And then I just did an FFT high-pass filter. And if we want to go into the FFT and take a look, so here's what the FFT of the flattened background non-glossy looks like. Let me take a shot of it. Let me bring up now the glossy image with the same recipe. And here is its FFT. So my suspicions were kind of confirmed here. You see a lot more intensity in the FFT further away from the center than you do in the non-glossy case. And further away from the center in the FFT are your higher image frequencies. Image frequencies can be thought of as intensity transitions. So a sharper image has more abrupt changes in intensity through the image, which means it has a larger number of higher frequencies through the image. If you envision a change in intensity as a line profile, so if I go in here and I take a line profile across the image, you've got a bunch of you've got sharp intensity transitions from very high to very low quickly. That indicates, you imagine a sine wave that behaved that way and continued through the image. That's a high frequency in the image versus something that goes down here to down here more gradually. That's a lower frequency in the image. So you've got high and low frequencies kind of merged together in the image to give you your overall profile, your intensity profile in all directions at all times in the image. It's kind of an abstract concept, but processing the FFT lets you sort out the different intensity transitions in the image. So what I did is I just made a little FFT filter here that erased a good bit of the lower frequencies. We inverted this filter and we just kept those low frequencies. That's what you get. So keeping low frequencies is kind of a blur operation on an image, where keeping high frequencies is kind of more of a flattening operation, where you're really retaining image intensity that sits at feature edges, at places where you have sharp transitions, and discarding the rest. So I figured if we applied the same filter to both the glossy and the non-glossy case, and then we measured the standard deviation of the total image after it's been filtered, then I expected that the glossy image, after keeping high frequencies, would have a greater standard deviation. It'd have a bigger spread in pixel intensity throughout the entire image than would the non-glossy image. So after filtering, the get Sean's images up here. it did seem like there should be some grayscale measurement that differed between these two images, and you're correct. John, the intensity sum and the intensity mean don't correlate with that. The glossy let's look at mean, because that's a big number. So we have an average intensity in this case of 107. Where if we look at the non-glossy, we have a mean of 114. So the problem with the mean intensity is that we need some other kind of normalization to come in and make sure that background intensity, since there's still a little bit of that makes its way into the high-pass filter, isn't affecting the measurements. Because overall, this glossy image, or the non-glossy, seems a little bit brighter to me than the glossy image. Which is why I was going to go with the standard deviation, because that kind of reports the spread in intensities, the spread in high-frequency intensities, instead of the actual average value of them. The sharper image should have a higher standard deviation because it's got more of the bright pixels in it relative to the dimmer background. So its histogram should be broader. Now there's the histogram of the non-glossy filtered image.
Does your software do anything on the luminosity of the surface?
No, we don't have any prepackaged measurements that would measure luminosity, but that's something we could add as long as we have the definition for what that measurement is.
Okay.
That's why I was trying to go after it, in this kind of a manner. Have you dealt with other packages that measure luminosity from an image?
That's one of the possible routes to try to measure gloss on an irregular surface like this, is just to measure luminosity through an image, and that seems to give some kind of a relative correlation. The shinier the object, the more luminous it is in terms of just the way that software interprets it.
Okay, well, we'd be happy to add measurements like that to the toolbox. No problem. Yeah, so let me look into that then and see how feasible that would be to add, and we can see how it correlates. I would be interested to try this kind of a approach here on some other images. The standard deviation of this filtered image.
Yes.
You have that
Let me take some additional shots of a few of the other products that we have marked differences in gloss level, and see if we can see if we have a similar reading.
Right. Yeah, any what I like about going after just the higher frequencies is that it does inherently get rid of any global brightness gradients or variations image to image, because those are low frequencies and they get discarded anyway. So you probably wouldn't even need a flattened background step in here if we had our high-pass filter set right. So if I broaden this out a little bit and used 100 instead of 50, these, let's even try 200, the mean intensity of these images might start correlating better. We're at 121 here on the glossy. Let me call this 3. Let's try this on the non-glossy. Did we encounter a bug? We may have. Oh, no, I think it's going. Recipes with FFT filters in there sometimes take a little longer to load.
Now, the images in their original form, you'll see on the one that has the higher gloss, there is a certain clarity to the surface. And the one, obviously, with the lower gloss has a duller surface, or not just duller surface, but it's really a surface effect. So it appears duller. And that's part of what we're trying to capture, is that, where you have that clarity translates into what appears to be greater definition of the actual product. But but the other part of that is that the embossing pattern, which has definable edges and everything like that, those are actually the same embossing pattern.
Right.
It's part of it's a matter of the clarity of the plastic when you place the emboss on it.
Okay. Got you. Okay. Well, yeah. If we had some additional samples, like you say, once we're able to take those, then we might better validate if this approach correlates.
Yes.
Okay.
Yeah, I agree.
We'll wait on that, but okay, we'll keep that.
That sounds good.
Very good. So Jan is on, I see. Am I pronouncing that right? I know a Jan who spells it the same way, so I just want to make sure I'm not.
This is a Jan.
This is a Jan. Okay. Hi, Jan. Very nice.
Hi.
Thanks for getting on. Yes, you saw a little bit of an example with FFT filtering here. Let me go back to. Let me take another fib slice example that has some pretty heavy milling artifacts on it. And these are in some ways similar to the lines that were in your image, Jan.
Right.
So what I ended up using for your case that I think worked pretty well was a directional FFT filter. Instead of using that circular disc like you just saw, we went in and made an FFT filter that erased frequencies that lay along these lines here. Since in frequency space, somewhat repetitive features that all lie in the same direction, in this case vertical, manifest as frequencies of high and low magnitude that travel perpendicular to those features. And that's what we see here with these this line and this band coming off in the horizontal direction. So we can take a line tool and play around with its thickness. You just take and draw a somewhat horizontal line, a little bit at an angle, so that we get that slightly off horizontal band, and say just erase those frequencies. That is too thin of a line, so I'm just going to up the pen size here to maybe 20. Now what I want to do is kind of straddle the center here, because the very center of the FFT has a lot of information from all directions. So I'm going to avoid going right through the center. I might want to make a couple of line tools here. Let me go just along this band, because I think these features here are just slightly off perpendicular. So if I erase those frequencies and then mirror the filter over the origin and erase again. Now you've pretty well eliminated those curtains. You end up with some remaining artifacts, but whenever I do this, I'm always amazed that I can even recover any of this microstructure that used to be completely obscured by those curtains. Now you could go in and run some kind of threshold here to sorry. Large window sizes have a problem sometimes. And there's a case where you might have gotten a little too close to the center and got rid of some image contrast. So we can, we're just going to actually keep frequencies in that area. Get some of the contrast back. Yeah, but little bit too much line left, so let's go take and erase a little bit more of this. Now your adaptive thresholding tool might be able to resolve some of those features. Clear this filter and make a new one. Comparing that to if we just ran the adaptive threshold right on the original image, just insert that below the filter. You really wouldn't have much of a chance of getting any of these features down here without getting rid of those curtains. So that is one application of FFT filtering, is getting rid of periodic features like that, artifacts, with trying to minimize how much you affect the rest of the image. And I think we can do a little better job with that line tool. I won't play with that anymore though. But that's I think the application that you were most interested in. We also saw with the high-res image before, the atomic column image, keeping spot intensities from the FFT to improve the clarity of atomic resolution images. And then finally we can use it sort of as a background flattening, or a even more aggressive background flattening when we have channeling contrast in the image. Channeling contrast meaning from an SCM image, these are all the same, all these gray tones are the exact same phase and composition. They only differ in intensity because you've got different local crystal orientations in these different features. So sometimes it's desirable to dump the channeling contrast, so to speak, so that all of the gray features have roughly the same gray level, and you can do that also with an FFT filter. Using a high pass of something like 5 is going to have more of a background flattening effect, but if you grow that filter out to something like 50, then it will have more of a overall channeling contrast flattening effect like that. So that's some applications of filtering in FFT space. Was there more that you wanted to see in that area, Jan?
No, this is good.
Good. Yeah, I'm happy to work with you further if you have some of your other iron particle images.
Okay.
That approach on. Did you think the particle finding worked pretty well on the example like that?
It worked pretty well. I was amazed that it was so much better than the wavelet filter that we used.
Okay. Well, that's Great to hear. Thanks.
Uh-huh.
Well, we had 3D kind of slated for the very end. Johan unfortunately had to go home, and he mentioned he was using Mipar for 3D reconstruction. Is there anyone else with us that wants to see any 3D? I think.
Yeah, me, from Justin Shan.
Okay, yes. Hi, Jashin.
Hi.
Yeah, so let's go ahead, and we've got about 20 minutes left. I will go show a reconstructing of a 3D data set here. But I think most are not going to be interested in 3D at this point, and you're of course welcome to stay on even if you're not. I see you on here, Meg. How are you doing? Not sure if you have audio. I don't think you have a mic connected, so sorry. Were you guys at? Are you able to talk now, Meg? If you pop up in the chat there. Okay, maybe she's stepped away. No worries. Yeah, so let's go ahead and finish off with a 3D data set analysis. The one that I have available, we look at the raw data. This is a fib serial section. We have two things interfaced and then some pores at the interface. So the batch processor does let you take care of your entire 3D workflow in one flow in principle, where you can define a segmentation recipe, the images to work on, calibrate your XY voxel dimensions, use this AOI tracking feature, which is helpful for dual beam fit data sets to correct the images, align the images, and make your reconstruction all in one flow. But in this case, I'm going to split the workflow into a couple executions of the batch processor so that we get a good feel for what's going on in each step. What I will first do here is make some new folders so we can start over with this data set. So I aligned what I mean is getting rid of any drift that might have happened during collection. So we'll run them through the alignment first for drift correction, and then we will do a final alignment afterwards, and we'll see what that looks like. So let me actually just load everything into a stack first, and we'll do the alignment in the 3D toolbox. All I'm going to do is say no recipe. Let me go in here to pre-aligned. Now I'll go take my raw images I'm just going to use the first 50 here so we move a little more quickly. And I'm not going to do, well, I'll tilt correct the images because they need to be tilt corrected by 52 degrees. I'm just going to make an image stack out of them. I'm just going to put all these into a Mipar stack file. There's no volume reconstructing that's going on right now. This is just a sequence of images. And that then saves an STK file that we can open in the 3D toolbox. And just look at the stack. So that's really the drift that I'm talking about. You've got, I think, a little bit of upward motion here of the cross-section of interest, just because this sample was collected inclined. And I think they use some beam shift correction to try to keep the area in the center, but it still moves up a little bit. But then you've also got this jittering that's going on during collection. So we can take our stack and just say align stack to first slice. And we'll use translation for the alignment. So this will calculate and then apply the translational corrections that need to be made using the entire content of each frame. And then we'll see where we are. So not only has it aligned, but it's also then cropped the aligned stack to the biggest area possible. You can look at it in the uncropped state, and you'll see now black boxes where the images had to shift. There's a lot of upward and leftward shifting that had to go on. Because what it's done is, you know, all of this content that's around the unmilled material, that's dominating the alignment. That's all going to be kept pretty stationary. Not perfectly stationary because it's still trying to align the image based on what's being milled. I was hoping to see just this cross-section of interest move up and not any of this other stuff. But let's try this instead. Let's undo that alignment. What we could do is just crop the stack to roughly include the area of interest. And now it's still jittering, of course, but we're now just confining our alignment to that area. What you can do is you can crop it like this and then align based on the cropped area and export those alignments and go back and load them on the original data set. But in this case, we might have just found our region of interest altogether, so we may not have to go back and reapply these to the original data set. But I can show you that if you want to see it. So we've cropped out the area of interest, and now we'll say align this crop stack to the first slice. Seems like it is sliding up a little bit towards the end. I don't know if including some of this extra content is confusing the alignment. So after playing with this some, I think my approach would be this. I'll reopen the original stack, and I'm going to confine my area of interest to something a little bit smaller. Make sure I only include milled material. Now this is what I'm going to align. Okay. Play feature seems to have an issue. That didn't align so well, did it? Let me try cropping one more time, but include some of these edges that can be used by the alignment as markers. And then I'll try running alignment on that. Okay, that seems better. So you can see what alignments were necessary. We had minimal Y shifts, no Y shifts in fact, just horizontal corrections, X shifts. So I can export the alignments as a text file. Into the pre-alignments. And now we'll go again, reopen the original stack. I guess we will save this one as the aligned stack. Oh, I already did that. So let's go back to the original stack now, and instead of calculating alignments from this original stack, we will align by loading alignments, and we'll go pick those ones that we just exported. And those will then get applied to the raw data, but they have been calculated based on a local area. Now from this full aligned stack, we could take and just select an area that we wanted to reconstruct. And now these are my images that I want to reconstruct. Maybe I want to crop these a little further. So now I'll take these images and I will export them into my final aligned so that I can make my segmentation recipe and then build a volume out of everything. Now let's go to the image processor and take one of those final aligned images. And let's say I'm after reconstructing the surface or the kind of the roughness of this interface. So let's start with a global threshold. Let's do a background flattening first, because there seems to be a little bit of a gradient. Using high-pass FFT filter instead. guess we'll go with that. We'll do that. Let's fill in some of the noise. Now, trying to avoid joining these little features here. So why don't we first, before we do any of that cleanup, let's do a very small erosion. That won't hurt things too much. And now we can reject small black features. And then grow things a little bit. And then erase white features. And then come down to a net 0. So we've eroded by a total of 2 and 5. So that's the feature that we've selected with the recipe. And now we can save this. Make a reconstructed 2 folder. Call that find a grain. And now we'll assemble the volume here. So we're going to use the fine grain recipe for the segmentation. Everything's going inside of this folder. We're going to give it the final aligned images to work with. The calibration factor, normally you'll have an image with a scale bar on it, or the microns to pixels should be in the tags of the TIFF file. I know from last time that I worked with this data set, this is 1125 microns per pixel. We don't need to tilt correct again. We're not going to make an image stack this time. We're going to make a reconstruction, and I think these are 50 nanometer slices. And I think I selected the wrong images. Final aligned to. Why do I have? Oh, I do have all 155 slices. Okay. So now we're taking our aligned images, we are running a segmentation on all of them, and putting both the reference data, the aligned images, or what I call the reference data in this case, so the reference data and the segmented data into a 3D volume that we can then visualize and measure back in the 3D toolbox. Okay, so now back in the 3D toolbox, we have a new layout here that I like using once you're done with any image stack adjustment. This will switch you to a recon-only layout that'll kind of reorient the tools. So you're just dealing with the reconstruction side. So I'm going to open the Recon 3D file that was made. Now we have the, well, that's not very good. It looked like there was some intensity. So we're looking at, we can look at the black and white view, the reference view, an overlay, or an outline view. And the first couple of slices were okay, but then it looks like there were some intensity changes that did not cause the recipe to not work so well on every slice. So we can go back and add a couple steps to the recipe and rerun it, but you are able to do segmentation directly in the 3D toolbox. So I'll show you how to do that. So let's call this one is from the recipe. This is this layer. Let's go ahead and add a new layer, and this will be directly from the 3D toolbox, and we'll just make it as a blank layer. So let's go in here and threshold the data set. Actually, first what we'll do is run some of these. Let's do a slice by slice auto contrast adjustment. So that should flatten out or normalize slice to slice brightness variations that are going on, which I think was the problem last time. So if we went back here in the recipe and added one of those steps, this recipe should work better as long as we adjust this value. And then let's do our background flattening on every slice. So we may need to, you see even a segmentation problem that seems as easy as this is tough to nail, especially in 3D. So instead of a fixed threshold value on every slice, go back to the recipe and let's have this set to be an auto threshold. Now I can make an auto adjustment. So for this particular slice, I'd like the threshold to be around 85. Auto is coming up with 116. So if I add a minus 31 adjustment, that'll take an auto threshold every slice and then subtract 31 from the result. And let me just resave this recipe. Rerun it. Are there questions from anybody while we're waiting for this batch to finish up in a couple minutes?
Yeah, I've noticed, this is Jan, throughout the whole webinar that you have not used the edge finding function at all. Is that a personal preference?
Yeah, I think so. It's probably, yeah, it's a personal preference and a bias of mine that's just developed over the years. When you use the edge finding function, I kind of use an edge finding function with the grayscale watershed that we did before with the agglomerated particles, and then I had to go in what was inside the feature and what was outside the feature. And that's what you end up having to do with the edge find, is you find the boundaries of the features, but then you need additional steps to tell Mipar what's inside and outside the features. So sometimes you can do that, but I usually prefer threshold approach over an edge finding approach. But that's a good observation. Okay, so now we have a new reconstruction file. We're not going to save any of this. Recon 01 has appeared. We've modified that first recipe by having an auto contrast adjustment step at the top, and then auto thresholding with an adjustment, since there seemed to be some slice-to-slice variability in brightness. And we needed that threshold value to be flexible. So the result now seems better. We have those holes in there that we can clean up here. So this I'm going to call from recipe again. And now we're going to duplicate this layer, and I'm going to call this cleaned. Every time you make any change to your segmentation, whether you make a new layer or you make an adjustment from any of these menus, with auto relabeling checked, it will do exactly that. It'll re-identify all the separate features. So if you don't need it to for that particular case, you can uncheck this, and that'll avoid that relabeling step. It'll just warn you that the number of features listed here might not be accurate. I want to go in and just slice by slice get rid of large holes like this. Thanks very much, Krishna. Please stay in contact. Send me any images that you'd like me to dive into in more detail. Thanks for attending. So I'm going to do a slice-by-slice rejection here. I think the value I set before just wasn't quite big enough. So if I make sure to get rid of white features that are under 20K, why not 30K? Then we'll just do that on every. That should get rid of those holes. Okay, and we have a couple of ones that are still here, and that's because they got connected to the outside. So here I might have to just manually make a couple of touch-ups. Take my pen tool here and fill. Now if there are a few slices in a row like that one, you can take your pen and say, now apply that edit from this slice to this slice, and even to this slice, and say fill. And now it's drawn that line on those 3 slices. These few need to be, oh. Now with those things closed off, we can again do our hole filling. We could just set something really huge. Or, no, we don't want to do that. Okay, so, one last. Let's just fix that. Oh, again, we missed that boundary. So we can just do a select 2D on the white feature here, double click it and say fill. Now I think we have a completed segmentation. Looks like there was a little one here that got found. Just select that 3D feature. it. Okay. So a couple of 3D viewing options. We can click on View Volume here. That'll give you a slice volume in whatever mode we're in. You can click through this volume from either direction. That's a way to take a quick look at your 3D data. If you wanted to draw a surface around that one feature, then you can use this tool here to just click on whatever features you wanted to render. So I'll just double click on that one. And then we'll draw a surface around the that one feature. We've chosen to include the free surface here with this checkbox, so it'll make a closed surface around the feature. And if you only have one feature in here, then for measurements you can just manually take them by clicking on that feature with the 3D measure tool. So then you get these set of metrics for that one feature. Or if you had multiple features, then you have a similar measure features like for 2 dimensions where you can check off the ones that you want and you'll get them reported in a spreadsheet. If you wanted the area for the volume fraction of selected features, those are under your measurements menu. Volume fraction in this case, 40%. All these other ones are possible. And by the time Beta 7 is out, we should have these other coloring modes re-enabled. Right now, the only coloring mode is a separate color for every feature. Those colors match the random coloring that's gone on the 2D side. But we will allow you to define a single color for the entire surface or use measurements to either color every feature by an average feature measurement or locally color the surface differently based on any of these surface measurements that you can generate: curvatures, thicknesses, local normals. There's more that we can talk about with 3D visualization. Mipar is not the most powerful tool when it comes to visualizing, so we support exporting either the surface as any of these file types or the entire volume into either an Abizo file format or a VTK format. Let's say VTK is the native format. Well, it's an open source format, but the open source visualization package ParaView makes use of the VTK format. So you can take your surfaces or your data sets and export those into VTK to use ParaView's powerful visualization and movie making abilities. If you have ParaView installed, then this Power Render feature is activated, and this lets you take, let's say, your whatever data type is shown here, and package it up into a VTK, and it directly opens it in ParaView. There's a more extensive 3D tutorial for visualizing up on the website as well. So that's probably where we'll end for today. Are there any lingering questions or comments?
Hey John, this is Austin.
Hey Austin, how you doing?
Yeah, I've been in email correspondence with you for a little bit here.
Yes.
So
I'm sorry, I did catch your email that you sent mid-webinar over with your grid. That's a good idea.
great. Yeah, do you think you have time to go over that real quick, or do you want to just get back to me some other time?
No, we can go over that here to finish, Austin. No problem.
Great.
Let me go grab your email here. Austin has been working with intercept length measurements of different 2D features, and I remember that.
Yeah, I'm actually working with Thomas and
Okay.
and Matt. We're gonna pop in Thursday.
Okay, good. Yeah, that's there.
Yeah, I mean the idea was simple. I just wanted to do a quick test for that intercept method, where I set up a square grid, and I assumed the square spacing was 1 or 10 microns, whichever I chose. But it seems to undershoot it by maybe 30%, 30 to 25.
Yeah.
I mean, it's entirely possible. It's just something I don't understand about it.
No, I see.
But I was just wondering if I could get your input.
Very good observation. Image here.
Yeah, that image should already be processed. It's a great tool, by the way. I really enjoy it.
Thank you very much. Okay, so yeah, this is one of you.
Yeah, precisely.
So, go and open that one.
Great.
And you noted, let me bring your email up here. Boxes in.
Someone's having a very animated discussion.
All right, great. So the boxes here were on his way in.
So if you go and use the ruler and do a feature measurement,
Yeah.
just any old square is fine.
Right. So you have, okay.
Oh yeah, sure. You can do 0.02. I think we'll do it. Yeah. I think that should approximately give you 10. You may need to calibrate it. Yeah, so there you go. Right, X and Y is about 1. Sorry if it's a little off.
Okay, no, I see what you're saying.
Yeah. So, but when you go over to measurements and do an intercept,
Right.
the feature one works great. That's excellent. Really cool. I actually didn't realize I could do that until today.
Right.
But if you go to measurements and then you
right.
do the intercept, like maybe rotating or at random, doesn't matter.
Right.
Gives you yeah.
Right, you get an average intercept that's less.
Yeah, it's just a bit lower.
Yep. Which I think is reasonable. So what you're doing with the random lines is you're drawing, of course, a random grid down on the image. So you are getting a few intercepts that are longer than 1, and they might cross the box.
Yeah, longer than 1 makes sense, right? I mean, you'll get shorter and longer.
A shorter and longer, right? Some intercepts that just flip
Yeah.
the box.
Uh-huh.
Like that.
Right, precisely.
Or less than 1. We can see all the intercepts that we're recording if we run this. Let's edit these parameters and say save all the intercepts.
Yeah, I've actually, well, I'll let you do that because apparently there's a way to plot the histogram directly.
Yeah, not in Mipar, unfortunately, but...
Okay.
Yeah.
Yeah, I've done it in Excel.
Excel,
in
okay.
Yeah, and I've definitely seen it. You do get a lot of clipping on those lower edges.
Yeah.
So I guess my question is that does that make this a good enough method for measuring that alpha left thickness?
Well, it's the method that we have used, like I spoke about, in that Gunderson estimation equation.
Uh-huh.
So you're going to have to be making a lot of assumptions either way.
Yeah. Yeah, and I understand. As long as you can assume and then sort of get a consistent answer. Though I mean, I think that for some feature, they'll want to be correct by like plus or minus 0.2. But seriously, human measurements are subject to all sorts of error and selection bias and things like that. So I even did a little experiment with a bunch of the interns here, and they only chose the nice ones, and they ended up missing a lot of the smaller ones.
Nice.
So this is a great tool, and it kind of matches up. But I'm just trying to find ways to get a nice calibration.
Sure. No, absolutely. Well, so.
Well, I guess calibration is the wrong word. Proof of concept, maybe.
Yeah.
With
here is that if you're going after so-called feature thickness, and you don't have features that approximate an infinitely thin, which is the case with these squares, then the Gunderson approach falls apart for using that to estimate thickness. So the Gunderson approach would take your mean inverse intercept, which is 2.73.
Okay.
Want to do 1 over 2.73. 0.73, and then multiply that by 0.7 to estimate your mean feature thickness. And we obviously think that's much less than if you transition these to
do you think that I mean, it might just be that we're running into a strange math problem where if you set up the grids and you do this, you get the undershoot. Does it work out better if you have a bunch of parallel lines instead of the square grid?
More on target.
I'm sorry, John. It's actually kind of hard to hear you.
Oh yeah, sorry, no problem. Yeah, let me take. We made a quick hypothetical grid of parallel.
Yeah.
Right. Image
here. I actually remember doing now that I think of it, I remember doing a quick test where I did some parallel lines, and I did a similar. It's not quite a thought experiment, but a similar virtual experiment, and I remember it doing okay.
Okay.
Yeah.
Yeah, Gunderson's paper that was written back in the 70s that went and tried to come up with a theoretical expression to go from mean inverse intercept to membrane thickness around cells. It relied on the fact that what you were sectioning through with images was a infinitely thin feature where its length was orders of magnitude greater than its thickness.
Yeah,
it
yeah.
Comes up with its theoretical inverse intercept distribution that looks like a triangle, so that 1 over 1.5 times 1 over the mean inverse intercept length is a good estimation of the thickness. You always have problems. You're always going to be, your factor, your Gunderson factor is always going to be a little bit less than 1.5 with experimental data, because by collecting the data experimentally, you've rendered it finite. You don't have an infinitely thin feature because it's confined to a 2D image. So we've done some theoretical experiments where we've taken 3D structures of plates and made them thicker and thicker and show that the factor moves further and further from 1.5 the thicker the plates get as they kind of move towards more rectangular features like what you simulated.
I see.
So if we took we could even do that kind of experiment here with this sparse grid, and maybe broaden the step size here. Let's dilate the lines a little bit.
Sure.
So if you have that grid of parallel lines where your thickness in this case is minor axis length of 0.88 microns. And let me what it's doing when it measures the minor axis length is it's replacing every feature with an ellipse and then measuring the width of that ellipse. So let me make sure that's not way off.
Okay.
Okay, yeah, so those are the ellipses. They might be just like a pixel wider than the actual. Oh, but we can, never mind, we can use a different metric. We can use x length here. Length x point. Wait, what the hell? That's weird. Why is that minor axis length so much?
Oh, John.
Yeah.
I know this isn't something you could do right now, but it's actually kind of hard to calibrate when that little bubble goes over your calibration bar.
Okay.
Yeah, I know I know that's probably not an easy fix. It's just something to keep in mind.
Yeah. Oh, and I appreciate that feedback. I've noticed that a couple times myself. So
Yeah.
We'll see if we can.
I mean, I'm sorry. I don't. Just a
No,
just a metallurgist. I don't know how to fix it, but.
Sure. That's a good suggestion. Yeah, when we're calibrating something, like we usually, if you zoom in more to the micron bar, then that bubble won't be so much in the way.
Right.
But yeah, it's a ease of use type thing, and we'll try to improve that. Thank you.
Yeah.
Yeah. So I think.
But sorry. One more note on that is
Yeah.
you might. I don't know if maybe this feature's just eluded me, but to have it kind of snap to the X and Y features of your image, that'd also be helpful.
The line.
So when you do that in ImageJ, you can hold Shift.
Yeah, right, and it'll snap. Yeah, absolutely. I'd like to add that feature.
Yeah, I know. I appreciate that you're busy.
No,
they're just notes.
Those are. I appreciate the suggestions. I meant I'd like to add that feature as developing this in MATLAB as we have. That's one limitation I've run into. But I'm trying to find a way around that because yeah, the shift feature would be very helpful to have.
Yeah.
Something that we should be able to do. It's not nearly as convenient as holding down shift, but you can. Once you make your line, if you right-click on your line and say constrain drag to horizontal, then it will go horizontal.
Okay.
So that's the workaround now.
That might be a good button to like throw on the side, I think.
Yeah, right, to make it obvious. Yes, I agree.
Okay. Yeah. Anyway, so we'll continue real quick.
Yeah, so that, I don't know, that minor axis length wasn't, I just did a manual measurement with that line tool, and I think the X length here of, why am I in pixels now? Huh. That's really weird. Okay. Oh, I have no idea what happened there. I better look at that. 0.15 microns.
Yeah. If only I could share the screen with you. Because the human error involved with measuring a micrograph is kind of surprising.
It's a little upsetting.
Well, the person, I'm just an intern, disclaimer, but the person before me, they took an alpha last measurement and they only did 5 measurements.
Yeah.
So, I mean, it's not really enough. And I had a bunch of interns. I told them, hey, just like choose your favorite 50, and they like the selection bias on that was a little bit ridiculous.
Yeah. Yeah, as we've gone to digital micrograph analysis, some things have become more objective, but then we've introduced, without even realizing it, other, like with these linear intercept measurements, what we're finding is that when you make them on digital micrographs where you've got pixelated boundaries, you end up sometimes having these 1, 2, 3 pixel long intercepts that you would never record by hand. You were drawing them by hand on a micrograph that can end up like really down your mean intercept length. So we've tried to work on coming up with a standard way of rejecting noise intercepts.
Yeah.
And that's why we have that
for
feature.
now, I'll just email something to you, but
Are you not able to share your screen at the moment?
oh, can I share my screen?
You can if you'd like to. If you go to your WebEx meeting room in the quick
No.
start.
Yeah, well, I can let you finish this one first if you want.
Yeah, do that. Yeah, so we've got 0.15 microns as the actual width of these lines. And if we run the intercept on here, we've got
yeah.
So 1 over 50662 times 0.667. We're down pretty close to 0.15.
Yeah, it's quite close.
If we moved and thickened these,
Hi there. Did you find your pen? I did find my pen. Did you? Sorry, John.
that's fine. So what was the percent error on that last one? We were at
That was 1.5 minus 1.3. So
right. So 0.02 divided by 0.15, 13% error.
Yeah.
And now I'll close that. The actual length is 0.29 microns. And when we run this, we get 1 over 2.74 times 0.667. 0.24 divided by 286. Sorry.
Yeah, 24. Yeah, I am. Thank you.
15% error. So as we go away from an infinitely thin plate, our deviation from Gunderson goes up and up.
Oh, I see.
So if we
Yeah.
run
Can I share the screen with you?
go ahead.
All right.
You should
That.
take over the sharing.
I guess. Yeah, I see it up here. Share my screen. Okay. Yeah, great.
There we go. Now I'm seeing it.
Hey, great. Yeah, as you can see, I was testing with a larger grid. Thanks for giving me your time, by the way. I appreciate it.
No problem.
Yeah, I'm working with Thomas and other people to get a standardized automated measurement. So let me
Give me
some preface here.
2 minutes if you could, Austin. I got to run and I'll be right back. Okay. Go ahead.
Okay, yeah, 2 minutes. That's fine. Hey, sweetie.
Hi. Are you out of work?
No, I'm still in work. I was lucky enough to catch the person who's running the webinar. He's running through something personally with me. So.
Wait, is the person on the site? Oh my god, it's so hot today. What's going on?
Yeah, he's Yeah, but anyway, he just stepped away for a second, so, but I just wanted to let you know that I'm going to give you a call later.
Oh, okay. Thanks.
Are you okay?
I'm just, yeah, I was just walking home, and I'm almost there. I'm like next to you today.
Okay. Well, he's not back yet if you want to talk.
Sorry,
Okay, Austin, I'm back. Sorry about that.
Okay, sorry, hold on.
No problem.
Okay. Good. So I just took this micrograph from a paper, and I've been talking to you about it.
Yep.
And so I've been playing around a little bit with it.
Okay.
And, oh gosh, I forgot this takes a little bit of time. Yeah, but I just took your method, and then the histogram that it gives you is kind of, at least just sort of the standard way, was a little bit, it felt like the alpha plate thickness was a little too thin.
Mm-hmm.
So I actually went back and I went through that image and I did about 300 measurements.
Okay.
So I can show you, for instance, how that looked like. And then I had all the interns do it too. Just give me a second here. All right, maybe mine's not. Oh, maybe it is. All right, yeah. So it was just a quick measurement. So this is just an image J where I went across a feature that I felt was a plate. Then I took a measurement.
Mm-hmm.
So that's going to be like a little bit noisy. So here's that measurement twice. This orange and gray, and here's everything by the interns, which again they went for nicer features, which had some error involved in it.
Mm-hmm.
I'm not sure why that's up there. Okay. Yeah. So if you just do like a random line measurement, you get, so inverse is black. I'll just do a little work here. Excuse the clutter.
That's okay.
This is 0. I just wanted to try out your measurement for a second here. I hadn't done this the Gunderson method yet. 7.3 equals I guess it was 1 over 1.5 times 1 over this, right?
Yep.
2.27. That's actually pretty good. Wow. I think as far as taking some average of this and getting that histogram. So I didn't realize that. That's spectacular. Well, thanks for pointing that out to me.
No problem. But no, it would be good to also look at the histogram of intercepts that Mipar output. Make sure there isn't like a massive peak of real small intercepts down at 1 or 2 pixels. Yeah, like that.
Yeah, I definitely did. And I think that there is a little bit, but it's not so bad. And it's a good point to try to cancel out the noise. I hadn't thought about that. Do you have any suggestions for what you would, what I would want to do?
Yeah, so you could do a couple of things. One, you could run a smoothing tool
Okay.
at the end of your...
Sorry, I'm going to take notes. Is that okay?
That's fine, yeah. So, if you mind actually, I can take control of your screen temporarily and just show you a couple of things on my part. So let me do that there.
All right. There you go.
Cool, thank you.
No problem.
Don't do anything nefarious.
I trust you.
So, yeah, okay, it looks like there was already a smooth features that went on.
Yeah, I tried that.
Okay, yeah, that's good. So, that can help reduce those intercept lanes, but we can also, we go into your, intercepts here. So the noise removal method that's default is reject less than or equal. That's just a truncation.
Yeah.
So put in like 1 pixel in microns is like 0.2 microns. So if you said like anything under,
I think anything under point like 3 to 0.4 is probably.
yeah, anything under 4 microns.
Yeah, it's probably fair.
Cut off that part of the histogram. And you'll also get in that measurement file that just got output. I'm not sure what directory we're in.
Sorry. Can I still control the mouse, or is it all
You should
yours?
be able to, yeah, go ahead and...
Oh, it's a bit laggy. I trust you. Or unless you want to surrender control. But here, why don't you go to the folder?
I just released control back. You should have
Oh,
it.
great. Yeah, it's I'm using my personal computer right now, which isn't very organized. There's been some problems with my work computer. And anyway, it was actually a lot easier to install this on my personal computer. Alcoa, they got
some. Yeah, I understand.
Yeah. All right, so it should be here. This will be the black intercepts. Oh, anyway, I guess I just need to go here. Get a new one.
Yeah, that'll work.
Yeah. Okay. Data. I have some weird formatting things for my computer. It's not the best computer. Do you want me to do inverse or just the normal?
Just normal is fine.
Okay. Oh, wow. Okay. I haven't seen that before.
2 columns there.
Yeah.
So now you've got the one with and without. And there are a bunch of zeros in the noise column at the end to make them the same column length. So you can just delete all the zeros that are at the bottom of it.
That's fine.
Delete those
It's actually
out.
not that much noise.
Yeah, not too many got removed.
Yeah, that may just be because I didn't choose enough lines.
You could make histograms before and after.
Yeah.
Or if that's all your, yeah.
Do you want to try that, or do you want me to do that later? That's okay.
You can throw them up there real quick. That's fine.
All right. We have 3,000 data points. We can do square root of n. Oh, well, maybe it's a good time to bring this up to you.
Yeah.
Because
I would not call your error bar the standard deviation of that divided by the square root of 3,000.
no. Absolutely.
Precision on measuring that one micrograph with 1,000 random lines, meaning that if you down another 1,000, you wouldn't expect the variation to be much more than that standard error, but it certainly doesn't tell you what the image-to-image variability is.
Right.
You can only multiple images and
Yeah. Anyway, there's a bunch of other metallography that's going to interfere with your actual error.
Right, you've got
right,
etching
because you're
issues.
Yeah. Machining, etching, like where your sample is relative to the center and the surface.
Mm-hmm.
Yeah. So let's go 0, 0 plus. I'm not quite sure where this goes over, so it's 3 over like 3 over 50. It's probably fine. Oops.
Oh yeah, you got to make your bins.
Yeah, my bins.
Yeah.
I'm sure you have something else that does it for you.
No, well, we've always used Kaleidograph here in my research group.
Kaleidograph.
Yeah. The CALEIDA graph, like kaleidoscope.
COLL.
Oh, sorry, here. KAL EIDA graph.
EIDA graph. Slide graph.
Sure, if they'll like support that these days, they might. That has a nice tool. You just paste in the data from Excel and click the column you want to plot and click histogram, and it just makes a histogram of it. I don't know why it's yet to be so simple in Excel.
Yeah, it's pretty strange that. Well, you know Microsoft.
Yeah. We are working on a data analytics tab, or a 6th application in Mipar that would do that kind of thing in addition to other like uncertainty analysis and neural network type
Oh yeah, that would be nice.
pattern recognition. But that's still a ways off.
That didn't work. Oh, I guess. Oh, you know what? I'm sorry. This is still in like pixels. No, it shouldn't be actually. That's strange.
Your bins there. Did you have? What's your bins called? Oh, yeah, there we go.
It seemed reasonable to me. But
Yeah.
there's I see a lot of 10s there, which is strange. It seems like it's in pixels. No, it should be bigger in pixels. I'm not sure what's going on there. This is reasonable. Let me try it one more time. Sorry, I'll try to be fairly fast.
It's okay.
If you like need to go at any time, feel free. That's fine.
No worries.
What? You know, sometimes I don't understand Excel. Okay. Yeah, that still looks the same. Alright, whatever.
I think those are, yeah. I mean, the mean intercept length was at like 7, so you're going to have some that are up at 10.
Yeah.
I don't know why the histogram looked so funky.
Yeah, I'm not sure. I guess let's go to like whatever that max is. Alright, hopefully that should just taper off. Might be a little excessive.
You may want to avoid all those zeros at the bottom for the input range.
Oh yeah, good point.
What cell is that? Uh, 7349. Oh, or just do that. Yeah.
Sorry, say again?
No, you're good. Just deleting all make more sense.
Yeah.
There we go.
What?
Range cannot be. Okay. Oh, they were in B.
Yeah, I guess,
There we go.
Yeah.
So
So it's applied some noise filter to it. Or has it? That's kind of
yeah, well, it's
odd
just
looking.
it's cut off everything underneath point 4. So there used to be a bunch of I don't know what.
You know, I gotta be honest, I'm not sure why it looks like that. It should be different. I think that I've done something wrong, personally. I'm gonna try to figure that out on my own.
Yeah.
That's fine. Well, but I'm gonna move on to another question I had.
Yeah.
So I might bring some of this up on Thursday.
Please do.
When Tom is here.
Yeah.
So one thing that this beta thickness,
Yeah.
it's sort of, it feels like that might be too thick. So why won't it work?
It's something.
Oh, yeah.
That should.
There you go.
That shouldn't.
I shouldn't have done it.
Is it letting you? What's it doing?
Yeah, it's pretty odd. I do other things?
Seem to be able to.
That's strange. Okay.
Can you go and switch images?
Yeah, okay.
Or
I guess we'll just go through this again. I really thought I saved the thing in there. But well, the point I'm going to get to is that it would be nice to have the adaptive thresholds, or maybe the erosion or dilution, I'm not sure which.
Yeah.
It'd be nice to have it calibrated to a thickness that the user measures.
okay. I see what you're saying.
You know, you go in and you take a measurement and you say, this is what I think the thickness, the beta thickness should be. And so based on that, that's how thick I think the line, well, I guess the black lines, once you transform, should be. Or that's like a maximum thickness cutoff. But I'm not sure really how easy that would be to do. But if it was suddenly Christmas and you were Santa Claus, that's what I would ask.
Okay. Well, I mean, what we wanted to add when you go to run your optimize tool is beyond the mutual information and the other metrics that are there is to be able to pick any of your global measurements and put those in there as the metric that you measure after every step in the optimization, so that you're basically doing a sensitivity analysis of that particular step on on some measurement. So if you measured, say, the mean white intercept at each step of the threshold value, then it would be then you could at least
anyway, it might just something to think about. I'm not sure if it's possible again, but if you could go in and you could, this is definitely not what it, how do you zoom in, by the way? Like this, yeah? Ah, okay. Yeah, so it seems like the thinning, correct me if I'm wrong, but it seems like the thinning transformation just brings it down to as few pixels as possible. Possibly 1, right?
Yeah.
Yeah. So I guess what I'm asking for is for a thinning measurement that lets me control the number of pixels. So instead of 1, like maybe 5 or something like that.
Okay. Gotcha.
Something like that.
Okay. For now, just right after your thinning operation, just throw in a EDM erosion of 5 and grow the lines.
Okay. So that, I forget where erosion was. It's over there, yeah. Road.
Sorry. Cancel.
Okay.
You're before, I didn't know you, right. So you're at the thinning step, you're double click on that so you can see the image. You're black, so do morphology, EDM.
Morphology, EDM, okay. Dilate.
Yeah. And then put in 5.
So that's number of pixels?
Yeah.
Ah, that's too big. Maybe 5 was not the one I wanted. Perhaps. So this gives you the number of pixels long that it'll dilate to.
Yeah. Well, it's a number of pixels. Hover over the depth with your mouse cursor, it'll tell you.
Number of pixels by which black regions will be grown in all directions. I see. Oh, yeah, so that's too big. We'll do like that?
Yeah.
Oh, yeah, that's great. So that's, that's excellent. That's kind of, I think, the workaround that you would want in doing this measurement.
Yeah, it is. You are forcing all your beta ribs to be the same thickness, and you are kind of using, you're using subjective measurements now to bias your parameter selection for your automated recipe.
Yeah.
But there's something to be said for that. You're kind of calibrating it in a sense.
Right. Yeah, that's really the only thing I wanted, and then I wanted to talk to you about that. In my opinion, with both those things taken care of, this is really great. This is excellent. Well, I suspect this is just a smoothing thing, and I think, but it'd be nice to connect some lines. That I think is, beauty in the eye of the beholder.
Mm-hmm.
Or something similar in scientific terms. But how would I do that? Is that just smoothing? So I would need to do a little more
To
connect some small interspaces.
Let me
You want to take the mouse?
take control here if I could, yeah.
Sure. That'll be the last thing, John. I really appreciate your time.
Austin, no problem. I don't know how well it will work. Something like this, maybe.
Yeah.
with the alpha lats in black.
Yeah.
We could try a watershed.
Okay.
And maybe you do a line thickness of 2 and try a weakness of 3. Yeah, it's doing what I was afraid of. Yeah, it's not quite connecting them how you'd like to see it.
Mm-hmm. Yeah, I think this problem in particular may just be something that's up to your microscope. I mean because this error is because you can't quite clearly see the lats.
Right.
Right.
Yeah. Right.
So it's some blurry gray, and when you're doing your adaptive threshold, it says, well, I must pick, so I choose this. Right.
Yeah.
Okay, so that's fine. That's really great, John. I really appreciate your help. Thanks so much. I think your customer service is wonderful. I think that's your biggest selling point, honestly, is ImageJ, but better and with customer service.
Yeah, not a bad way to put it. I appreciate it. That's what we're trying to do.
Yeah, yeah. Much better than ImageJ, may I say. I really like the recipe thing. I think that's a great idea.
Thanks. Thanks a lot. Yeah, it's kind of the main technology. We try to have some other nice user experience around it, but we're growing all the time, and I mean, it's great to have a user like you because you give such honest and helpful feedback. So really, never apologize for the time. You're always welcome to ask questions, and
That's great.
make it to Thursday's webinar if you're able to with Thomas.
Yeah, I'm going to do that, and I think I submitted this exact image.
Yeah.
But I might not see this. I might move on to something else. This is great.
Okay.
I'm probably going to prepare a presentation to give to some of the higher ups at Alcoa to sell them on this.
Okay.
Yeah. Well, first going to do some more test measurements and such.
Sure.
And I'd appreciate if you could look that over, since I'm selling it. You don't have to do that much. Just any tips you have. That'd be great.
Okay. Problem.
Yeah. I mean, I would like to at least have, my goal for the summer is to at least have one copy on one of their computers.
Sure.
To show them that you can throw an intern on here and he could process your images for you.
Yeah. Oh, I think they would like to see that.
Yeah. Okay. All right. Thanks a lot, John.
No problem.
I think I'll see you on Thursday.
Okay. Send anything in advance if you wanted to see anything covered, and I'll make sure it gets in there.
Great. Thank you.
I'll talk to you soon then, Austin. Thanks a lot.
Yeah, talk to you.
Yep.
Thanks, John. Bye. Oh, I don't know if